All right, now we're going to talk about something called a chain rule. Because up until now, we've been um, we've been talking about functions that are differentiable, like that. That's easily differentiable. So the derivative of that is 4x to the third. Or we talk about trig functions. The cosine of x. The derivative of cosine of x is negative sine of x. But what happens if we have something? How do we differentiate a composite function? F of g. And to recap, a composite function is a function within a function. How do we differentiate a function like that? We use the chain rule. And this is going to open up, these next two sections are going to open up a whole bunch of different ways we can do differentiation with functions that don't look like we can do it. The chain rule basically says when you take a derivative of a composite function, when deriving a composite function, you take the derivative of the outer function with respect to x, and then take the derivative of the inner function with respect to x. We introduce substitution here. We introduce substitution. Example, if my function was 3 over 2x, I can look at this as a composite function. This is the same thing as 1 over 2 times 3x. It's a function within a function. So I will define this part as u. I'll say u equals 3x. So my function now looks like this. 1 over 2 u. And remember, u is equal to 3x. So we have three parts that are going on here. F of x is equal to 3 over 2x. That becomes 1 over 2 times 3x. That becomes 1 over 2 u. So to make it easier, make this a y instead of f of x or y. So the derivative of our function so we're going to try to find dy dx. We're trying to find the derivative of y with respect to x. But our function is made up of this. Because we have a function within a function. So what we have to do here is the outer function is dy, and the only variable inside there is u. So I'm taking the first part, I'm taking it with respect to u. So that's the outer function. Now I got to multiply by the derivative of the u. So I take du with respect to dx, because what is u? U is 3x. You have to build up your chain rule. That's what we call a chain rule. It just follows on. So the dy dx is actually f of u, and then that's what u is. So I take the derivative of the function with respect to u. So in this case, what is dy du? Look at this right here. If I'm taking a derivative with respect to u, here's u. What's my derivative of this function? Treat it the same way as x. It's just 1 over 2. Because this has a power 1. It comes down and goes to 0. It disappears. So dy du is 1 over 2. What about du dx? Du dx, here's what u is. What's the derivative of this one? It's just 3. Huh. So multiply these together, we get 3/2. But remember, our original equation was 3 over 2x. What's the derivative of this whole equation? What is dy dx? 3 over 2. So it equals. So this is just an example that shows you how it works. We start off with a basic easy equation. And this is how we break it up into pieces. So now let's look at larger examples. Example 1. Y is equal to 3x squared plus 1 squared. Find y prime. No, we can't. This is no longer the same way we used to have it. We used to have x to the power 2. That was easy. But now we have this function squared, but inside there is another function. So the first thing we got to do, what is u? That's the inside function. So what would du dx be if we had that? What's the derivative of 3x squared plus 1?
3 squared.
No, the derivative of x. That's what we're looking for. Bring the 2 down. So it's 3 times 2, 2 minus 1. The 1 disappears. So it becomes 6x. So du dx is 6x. Remember, what we're trying to find is this. That's the derivative of a composite function. We just found this part. That's this one. How do we find dy du? Well, if this 3x squared plus 1 is u, what we have is u squared. So what is dy du with respect to u? To u. You have to rewrite your original equation as a form of u to some power. Now we have our two parts. So dy dx is dy du is 2u. Du dx is 6x. Two times 6 is 12. X times u. Well, what is u? What is u? Right. So that's 3x squared plus 1. Distribute. So 12 times 3 is 36. X times x squared is x cubed. Positive and positive is positive. 12x times 1 is 12x. So this is my dy dx. That's my derivative. We're right now constructing it. So we're going to show shortcuts to this and be much easier much later on. In a minute, I'm sorry, but it's just in a little bit. So I'm going to show you shortcuts for this in a minute. So here's the theorem. The chain rule. It says if the function f of u is differentiable at the point u equals g of x, and g of x is differentiable at x, then the composite function f of g of x equals f of g of x is differentiable at x and the composite function. Here's where it comes into the shortcut, the formula. Because we know the composite function is f of g of x, then the derivative of this thing, then the derivative of this composite function is the derivative of the outer function, leave the inner function alone, and then times the derivative of the inner function. There is the shortcut for it. Take the derivative of the outer function. So you don't have to do the du dx anymore. So this is our shortcut. That, of course, was Newton's. Leibniz notation for this was dy dx, that's the derivative of the function, is equal to dy du times du dx. They both mean the same thing. Here. So again, it's take the derivative. Well, let's look back at the last example we just did. Y is equal to 3x squared plus 1 squared. So the derivative of this function, what's the outer function? The outer function here is squared. So what's how you take the derivative of it? Bring it to the front and subtract 1, which is just 1. That's the derivative of the outside function times the derivative of the inside function. What's the derivative of 3x squared plus 1? 6x. Now multiply everything together. 2 times 3x squared, so it's 6x squared plus 2 times 6x. 6 times 6 is 36. X squared times x is x cubed. They're both positive. 2 times 6 is 12x. it makes it a lot easier because you have to find, you have to take the du, dx, dy, du. It's just take the outer times the inner. Example 2. It says an object moves along the x-axis so that its position at any time t, for t being positive or 0. So an object moves along the x-axis so that its position at any time t, where t is greater than 0, is given by this equation. Why is there a t inside the parentheses? Why is there a t inside? How come there's x in front of here? How come there's a t inside there? Where is this object moving? Where? What direction? Where along what? It's along the x-axis. So I want to know what the position is anywhere on the x-axis. What does t represent? Time. So that's the only value that changes is time. So the position is dependent on the function of time. So the question is, find the velocity of the object as a function of t. What does that mean? Find the velocity of the object as a function of t. What do we have? What do we need to find? And how are they related? How are they related? Sit here and wait. You said we have to find the first why. Why is the first derivative velocity then? Because what's given in the question, an object moves along. That's a position function. That is your S of t, your position function. As S moves along, the velocity is the derivative of your position function. That's why you take a derivative of it. Obviously, we're in the chapter of derivative. You can just spit out derivative as an answer. It's going to be right. But the question is why? That's what I want to know is why is it the derivative? Because I gave you the position function. This is where the object is anytime along the x-axis. How fast is it moving? The velocity. So now I got to find the first derivative as a function of t. Because the first derivative of the position function is the velocity function. So using what we just talked about, how do we take a derivative of this function? We just talked about it in the last half hour. See if we can do it, if your memory is that long.
So we put like cost.
What's the rule? We just read the theorem. You have to use chain rule. Because cosine's a function, inside the function, we have to use a chain rule. What does a chain rule tell us to do? Okay, yeah, that's going the long way, but we just did the shortcut with the chain rule. I just gave you the theorem.
Oh, G X equal to.
Okay, yes, but now how does it relate to our function here? You're right. Everything you're saying is absolutely correct, but you haven't given me the answer of how we're going to do this. We don't have a u anywhere there. We don't have a g. All we have is cosine t squared plus 1. How does the chain rule tell us to solve this?
So we put the derivative of the cosine.
Which is, what's the derivative of the cosine? Negative sign. Leave the inside alone. Times, which is 2t. Right. The chain rule theorem tells us take the derivative of the outside function times the derivative of the inside function. Right. So our answer here is our position, our velocity is negative 2t sine t squared plus 1. It's a function of t. Okay, let's look at the next example. Again, this is the stuff you have to listen for when you're taking notes. Because just copying what you have here, I'm sending you these notes. You don't have to write anything. I'm sending you these notes. You just have to listen and understand what I'm talking about. That's a small request. The outside inside rule. Basically, this is what we're saying. The derivative of our function is the derivative, remember, we have f of g of x. So the derivative of using the chain rule is you take the derivative of the outside, leave the inside alone. I didn't do anything with g of x. Now I take the derivative of the inside. That's what we just talked. That's what the chain rule theorem tells us. Do the outside of the function first, and then take the derivative of the inside of the function. Sine squared, sine of x squared plus EX. Find the derivative. Or differentiate. Okay, so with what we just talked about, what is the answer? Y prime is equal to the derivative of sine is cosine. Very good. So what's the derivative of e to the power x? E to the x. There's another example of the chain rule. The derivative of e to the x is e to the x times 1, which is e to the x. Why is it times 1? Let me give you another one. If we had this function, e to the x squared, it would be e to the power x squared times 2x equals 2x e to the x squared. Where did this come from? Where did this come from?
Come from exponent.
The derivative of the exponent, right? So what we have here in general, no matter what we have as an exponent, the derivative will always be EU du dx. That is a general rule for derivative of exponential functions. Just pretty much always start off, write down what you have, then take the derivative of the exponent. That's what we have left. So far, so good. Okay, let's see it now with the trig function. Example 4. Y is equal to E cosine X. Differentiate it.
Sine x e.
Nope.
Oh. Okay, now another one. Negative sine x times e to the x.
Very good. It wasn't sine X, it's negative sine. Remember how I told you all how to memorize these trig conversions? The y-axis is the sine. The x-axis is cosine. Derivatives go this direction. So the derivative of cosine is negative sine. We talked about this last week. We can do higher derivatives. G of t is equal to tangent 5 minus sine 2t. How do we do this? Because to differentiate it, we have to first find what? The derivative of tangent. What is the derivative of tangent? So in other words, if y is equal to tangent, what is y prime? How would we figure that out? Tangent is sine over cosine. Okay, then what do we do? Because we have to find the first derivative. What kind of equation is this? It's a quotient. So do we know any rules that we can take derivative of that? What? The quotient rule, right? The fishy thingy. How do we do that? We have F, G, F prime, G prime. I'm glad that's stuck. So what is F? That's the numerator, and the denominator is G. So the derivative of sine is derivative of cosine, negative sine x. Since it's a quotient, we put a minus sign. We subtract. So we got cosine times cosine is cosine squared minus, that's this one, sine times negative sine, which is negative sine squared x. Negative and negative becomes a positive. So what does that equal? That's the first identity, the trig identity. Very good. So this, is that our derivative? No, because it's a quotient, this goes on top. And whatever's on the bottom, we square it. So if y prime equals 1 over cosine squared, what does that equal? What's 1 over cosine? Secant. Since it's squared, this is secant squared x. That's the derivative of tangent. So the derivative of tangent is secant squared 5 minus sine 2t. That's the outside. Now we have to take the derivative of the inside. We multiply. What's the derivative of the inside? We have 5 minus sine 2t. If this is equal to y, what does that equal? What's the derivative? Derivative of 5? 0, that disappears. Derivative, now we have another chain rule. So the derivative of sine is cosine 2t times the derivative of the inside, 2. So it equals to negative 2 cosine 2t. So that's the derivative of the inside. We have negative 2 cosine 2t. So the derivative, what do we have here? We have negative 2 cosine 2t times secant squared. Not much we can do with this. Not much we do. So that's our derivative. So it's positive. I mean, it's possible to have chain rule within a chain rule within a chain rule. There's no limit. So far, so good. Can we use a chain rule of a power function? Or is everybody okay with that last example? That one had a lot of moving parts. We took the derivative of tangent, which is secant squared, left this alone. Then we took the derivative of this, which gave us that. And nothing can cancel out. We're done there. The chain rule with powers of a function. In other words, this is the chain rule. Remember what the power function was? The power function said what? If x has an exponent, that's the power. The derivative is what? N minus 1, minus 1 from the exponent. So that's if the base is just x. Now, what if the base is a function of x, where u is equal a function of x? It's no longer just x, it's an equation. So how do we find the derivative of a power function using chain rule? Well, the same way. It's actually, if you think about it, we took the power down here as factor 1. That's the outside. Times the derivative of the base. What's the derivative of the base? What's the derivative of x? So that's why nothing changes. But since the base, is now a function, we have to take du with respect to x. We have to take the derivative of the base also. Let's look for an example here. Ooh, a bunch of them. A. Y is equal to 5x cubed minus x to the power 4, all that to the power 7. Find y prime. Remember, y prime is the same thing as dy dx. So what's my first step? You have the rule on top of this screen. Bring the power down, which makes it 7 5x cubed minus x to the fourth. Subtract 1 makes it a 6. That's what that says. Now do what? What does this tell us to do? Yeah, take the derivative of the base. What's the derivative of 5x cubed? 15x squared minus the derivative of x to the fourth, or x cubed. Very good. Now we can multiply it by the 7. So 7 times 15, 35. So it's 105x squared. 7 times -4, so it's -28x cubed times 5x cubed, x to the fourth to the power 6. There's our derivative. You have to practice this stuff. I mean, it's not going to help you much if you're even considering thinking about taking calculus 2. You better know this stuff inside out. If not, because calculus 2 is the most difficult of all the calculus. It's like 6 times more difficult than this stuff. If y equals 1 over 3x minus 2, find y prime. So what's the first thing we got to do with our function? There are 2 ways you can do this one. What are the 2 ways? And let's look at both ways, see if they're the same answers. What's the first one? What's the first rule that jumps out of your face? What are we going to do first? The quotient rule, obviously, yeah, because it's a fraction. So f is the numerator, g is the denominator. Derivative of 1 is what? 0. Derivative of 3x minus 2? So since it's a quotient, it's a minus. We have 3x minus 2 times 0 minus 1 times 3. 0 minus 3 equals -3. That goes on top. What goes on the bottom? Very good. Whatever we have on the bottom, square it. Actually, here's a question. If this was squared already, all we would do is just add 1 to it. every derivative of a rational function of a quotient, you add one to the denominator. Can you guess why? So this is our answer. I'll show you why. Because this is the way we're gonna do it using the quotient rule. I mean, using the chain rule. What's another way of writing this equation? We can rewrite this as x to the power -1. The derivative, bring the power down and subtract 1. Since that's a negative exponent, it goes down, it drops. Because of this, it always just increases by 1 on the bottom. So in the second derivative, our denominator, instead of x squared, it's going to be x cubed. And whatever the top's going to be. All right. So with that example right there, let's solve this one again using this example. Instead of using the quotient rule, we can rewrite this as a negative exponent. And the derivative, see how fast this is much faster than the quotient rule. Because here, what do we have to do first? Bring down the exponent, which is -1, and do what with that exponent? Subtract 1, which makes it -2. And then what? Now we got to take the derivative of the inside, which is just 3. Which becomes -1 times 3 is -3. And 3x minus 2 to the power +2. Because that's all a negative does is change the location of it. You see how much faster the chain rule is than the quotient rule? It just gives us another alternative to solve these things. Y equals sine 5x. Find the derivative. So what's the first thing we do? Can we use the chain rule here? If so, what is the chain rule? What does it tell us to do first? Any wild guesses? Yep, take the exponent, put it out in front. So it becomes sine to the what? Because you subtract it. That's the outside. And then what? All right, then the derivative of sine, which is positive cosine. So the answer is 5 cosine x sine to the 4th x. And that's our derivative. How does this fit into the quotient rule? I mean, in the chain rule? Because sine n to the power of x is the same thing as sine x to the power n. That's a chain rule. So here's another identity that you have to remember, that exponentials with trig functions. Y is equal to e to the square root 3x plus 1. So what's the derivative? Well, first, always just put that. So it's going to be that. That's the derivative of e. Times what? Now you have to take the derivative of what part of it? Where's the only part with an x? The exponent. So now we have to look at this equation. Let's make that g. Now we have to find the derivative of this one. How do we do that? Well, first off, we have to rewrite it. How do we rewrite it as a exponential?
So black hole is equal to half.
Right, so the square root, since there's an invisible 2 there, that's the root, that's the denominator. If it was a 5, the 5 would be on the bottom. There's your conversion for exponentials. For radicals. Whatever's inside this root, that's the root. If there's nothing there, it's a 2. So how do we take a derivative of this function now? Bring down the power. 3x plus 1. And do what with the top? Subtract 1. Subtracting 1 is the same thing as 2 over 2. So 1 minus 2 is negative 1/2. Then what do we do? So that's the outside. Then we got to do what? The derivative of the inside. What's the derivative of 3x plus 1? 3. So our derivative, the 3's on top, over 2. And this has a negative exponent. So it's 3x plus 1 to the power 1/2. Positive. Which means it's a square root. So that's the derivative of our exponent. So our final derivative just rewrite it this way. And there's your answer. All right, let's take another example. You have to remember the procedures for the chain rule. Take the derivative of the outside times the derivative of the inside. Take the derivative of the absolute value function. This is an interesting question. Do we have a formula for the absolute value? What do you think? If we had a formula, what do you think it would be? Because what does an absolute value function do? The absolute value does what? Ever see it? Anybody ever not see this before?
I've seen this one, I've seen this one before, and I understand it's like, if, I understand this one because just.
What's that? Well, what it does, absolute value tells us the distance, how far a number is from the center, from the origin, from zero. Does distance have a sign? No, if I'm 5 feet in front of you, you're 5 feet behind me. You're still 5 feet away from me. At distance is an absolute value. It's not neither positive nor negative, it's just a number. So when you square a number, it gets rid of the negative. When you square root it, it brings it back down to its regular size. So there's the formula for the absolute value. So what would the derivative be of this function? And no, you can't simplify it by saying that the square root and the square cancel out. What does the absolute value graph look like? It's a V. So for us to find the derivative, what do we got to do? We have to rewrite that equation this way. So using the chain rule, we have 1/2 x squared, subtract 1, which is 2 over 2, makes it negative 1/2, times the derivative of the inside, which is 2x. The negative exponent simply means it goes on the bottom. So we have 2x over 2. This one can be rewritten. So x squared to the power 1/2 is the same thing as the absolute value. The 2's cancel. So the derivative is x over absolute value of x squared. As long as x does not equal 0. Let's look at this. What is the first derivative define? What does it tell us about an equation? What does it find for us? What does the first derivative tell us? The what? Okay, yes, rate of change, but what does it tell us? Back in the basics. When we first started talking about this stuff, when we first started this class, what does the first derivative tell us? What is another thing for a rate of change? Look at your notes. What is it? Think of how we started this stuff. What equation did we start off learning? The slope, yeah. So what the first derivative tells us is the slope. Because it has a point at 0, it's not differentiable at that 0 point. Because there are 5 conditions, and having a corner, a point, is one of the conditions you cannot differentiate at. So what do we know about this? If this is our slope, what does our first derivative tell us? So the first derivative is x over absolute, not absolute x squared, it's absolute value of x. But remember, the square root of x squared is absolute value of x. From the left side, what's the slope? What's that? It's negative what? Yep. So from the left side, it's -1 for any x less than 0. Think about it. If I put -2 inside there, if I put -2, top is -2, absolute value of -2 is 2. So negative over a positive is negative, 2 over 2, so it's -1. That's the slope. And what is it on the right-hand side? It's +1. So there's your definition for the rate of change, the derivative of the absolute value function. Everybody okay? So again, you notice we're doing a lot of basic algebra manipulations here. Absolute value is square root of x squared. Basically trig manipulations. So another one. Show that the slope of every line of every line tangent to the curve y equals 1 over 1 minus 2x cubed is positive. show that the slope of every line tangent to the curve y equals that is positive. At any point you pick, it's always going to have a positive slope. How can we prove that? So in that question, what does it tell us we have to find first? Y.
Good. Did I say, I say the slope?
Yep, because it's saying is show that the slope. Remember, the slope equals the first derivative. So we have to first, before we do anything else, find the slope. And each of these slopes are of the line tangent to the curve. So that's just redundant. So the first derivative, this is the definition of the first derivative. The slope of the line tangent to the curve. So the first thing we have to do is take this equation and find the derivative of it. How do we do that? What's the first thing we got to do? Yeah, let's rewrite it first. So we use the chain rule. Because the top is a 1, it's easy to do this. So the derivative is what? -3 times 1 minus 2x on the power. -4 because we subtract 1 times the derivative of the inside, which is -2. So -3 times -2 is +6. Remember, it says show that the slope of every line tangent to the curve is positive. So how can we do that from here? Show that the slope of every line tangent to the curve is positive. If we look at a graph, we have 3 sets of numbers we have to look at. Negatives, positives, and 0. If you put a negative number in there, what's going to happen to the slope? What's the slope going to be?
So,
Let's say we put -1 in there. So we have y at the y prime at -1. So we have -2 times -1 is +2. So it's 6/3 Are there any negative numbers in there? No. Because the top is positive, the bottom has a positive exponent, it's always going to be positive. So because of that, every point you put in there is going to give us a positive slope. Because the top and bottom are both positive. even if we look at the graph of the function, it's a cubic function, but it's 1 over. So what this thing looks like is like this. But it's a rational expression. So what happens here? It's a cubic function. Cubic functions look like this. Every point on a cubic function is positive. Oh yeah. Plenty of time. And the last example of this section. So when we, up until now, our X up until now, all of our values for X were considered radians, not degrees. Think about it. If we ever, when we said, when we did the unit circle, this is cosine at 0 is 1, at pi over 2, at pi, 3 pi over 2, 2 pi. We've always looked at, but not really at degrees. What if we're given in degrees? What if X was given to us in degrees? How do we convert that? Well, let's look at this first. First off, we know that 180 degrees is equal to what? Pi what? Pi radians. So if we look at this, when we convert from a degree, then what we look at here is we have whatever X degree we have times pi over 180. That's the conversion from radians to degrees and degrees to radians. Which we have an example here somewhere. Let's say we had this, whatever, this is some degrees, I don't care what it is, it's some value. How would we go about and use that? How would we convert that? So the first thing we would do, if we're given in degrees, is convert this to radians. This formula right here. So we have x pi over 180. Oops. So the derivative would be what? What's the derivative of sine? Cosine x pi 180 times the derivative of the inside. If the inside is u, x pi over 180, what is u prime? we're taking this with respect to X. The rest of this stuff is just a constant. What's the derivative of X? 1. So this is pi over 180. So this is pi over 180. So the derivative would be pi over 180 times cosine x pi over 180. Which means our derivative is pi over 180 cosine of x degree. This is how we would do the degree conversion. Yeah, we can do this. Any questions? Again, if in the past you haven't been looking at your notes and staying up on your homework, it's only going to get more difficult as we go through. Again, I can't stress this enough. And that's also why I tell you that at the end of the semester, don't ever dare ask me for extra time or more bonus points or whatever. I'm simply going to say, no, you had 16 weeks to do this.